Okay, so chapter 12 has homework for you as always. And now we start to talk about liquids and solids. They are significantly different than gases because they are so much closer together that we see a strong increase in intermolecular attractions. Now, intermolecular attractions were discussed before. We said that we had a couple of basic types. The London are the induced dipole or temporary dipole, which induces a dipole. Then dipole, and those are the only force that occurs in nonpolar molecules. Dipole forces are forces with polar molecules, and hydrogen bonds exist when we have materials that have fluorine, oxygen, or nitrogen actually bonded to hydrogen within the molecule. These bonds within the molecule are so polar that they allow bonding between the molecules or between the ends of long, twisty biology molecules. We talked about that previously. And London forces are the only forces in the nonpolar compounds. In dipole, there has to be a dipole or it has to be a polar compound. And when we think about this, it makes sense because we have this variation. Now, I don't know if you can see that. I think you can. This is representative of a gas. We just have molecules bouncing around in a container, and they're not interacting with each other. There's a lot of distance between them. But when we cool the molecules off and we push them together like a liquid, you can see the liquid molecules are moving around, but they're having a lot of interaction with each other because they're so much closer together. So those intermolecular forces count. And when we get to a solid, the molecules are packed into their position in the crystal lattice. So there's very little motion and there's a lot of interaction because they're touching all of the time. So the intermolecular forces are even stronger in a solid than they are in a liquid and considerably stronger than in a gas. So I think that's kind of a nice visual to help you with what's going on. So now we're going to be looking at how these intermolecular forces affect physical properties. So when we think about intermolecular forces increasing, we're going to look at a variety of physical properties and see how these change with changes in intermolecular force. So the first one is the surface tension. And the surface tension is apparent elasticity. It is the behavior of the molecules at the surface due to uneven intermolecular forces. And when we look at this, we can think about a container that has a liquid. Across the top, we have a row of molecules that are sitting on the top. Down here, I have molecules everywhere. So if we have a molecule down somewhere in the container, that has intermolecular forces from neighboring molecules all around it. There are molecules in front of it, behind it, to the left, to the right, on top. So it feels very even intermolecular forces. But if a molecule is at the surface, there are no molecules up here to attract it, and so it feels an uneven force due to the molecules around it and below it. This causes these molecules to want to move down into the container to equalize those forces. And this will result in the surface becoming concave. Now, when that happens, when we have that disturbance, if we have a high intermolecular force and we have a high surface tension, more molecules are going to move in to equalize that pressure. So it's like the guys down here are saying, oh, disturbance at the surface, let's go up there and check things out. And when they do that, this causes the surface to become convex, and the liquid will actually start to move up. This is most noticeable when we have a really small capillary. So if we have a very, very skinny tube, a little skinny glass capillary. Now this actually works with bar straws. Okay, you know, if you go into a establishment, they have those skinny little tiny bar straws, not like the big straw you get at McDonald's. This will actually work with those. They work with those coffee stirrers too. Although the ones I've seen recently, the coffee stirrers don't have those little tubes anymore. The ones I've seen lately are just solid, and my understanding was that McDonald's quit having those with the holes because people were doing Coke with them. I heard that. I don't have any experience from that, but yeah, a cough, those like the ones that have the two little tiny capillaries, it'll work with that. So what happens is you have such high surface tension, the molecules are hanging on, that when you have something, the liquid in the capillary will actually rise up above the level of the liquid in the container. And we call that capillary rise. And this is a measure of surface tension. So the liquid will rise until the force of the tension going up is equal to the force of the liquid pushing down. And things with high intermolecular forces have high surface tension and high capillary rise. If something has low surface tension, it just spreads out completely and wets the surface. If it has high surface tension, it beads up and it doesn't wet things. And when we talk about wetting, we're talking about the liquid spreading out completely. If you ever go in the car wash, you go through the car wash, it scrubs your car nice and clean, you get to the rain part at the end, and as you're getting rinsed off, you can look and you'll see that the water is not spreading out. The water is actually beating up on the surface of the car. Or you'll see this if you've treated your car with Rain-X. Sometimes that water just beads up. That's because of the high surface tension of water, plus the Rain-X coats your vehicle with something that makes it less likely to have the water spread out. But that's because of the high surface tension. So surface tension increases with increasing intermolecular forces. We also talk about viscosity is another property. And I'm just writing this on the board so you can kind of get a view. Intermolecular forces increase, surface tension increases. And also viscosity, that is resistance to flow, and that increases with increasing intermolecular forces. So when we think about viscosity, this resistance to flow, think about pouring milk. Imagine that you're pouring milk into a glass, and you all know what that looks like. Now think about pouring honey into that glass. The honey kind of hangs there, and it pours really slowly. That is because honey has a higher viscosity than water. And so the molecules have a higher intermolecular attraction, and they flow more slowly. Now, I brought something to show you to demonstrate surface tension, but unfortunately, I can't do it on the video without making a giant mess.